So the problem is sketch the root locus of the system having open loop transfer function g of s h of s is equal to k into s square minus 2s plus 5. So the first step is to identify the open loop points and zeros. Here open loop points are minus 2 and plus 0.5 and zeros the roots of this quadratic equation, that is 1 plus j2 and 1 minus j2. So the number of branches is equal to, here number of poles and number of zeros are equal, it's equal to 2. Therefore the number of branches is equal to 2. Then so mark these poles and zeros in the S plane. So 0.5 one pole, minus 2 another pole, 1 plus j2 1 0, 1 minus j2 another 0. So mark all the poles and zeros in the S plane. Then identify which all points in the real axis are the part of the root locus. So take any point in between 0.5 and minus 2. To the right of that particular point, any point, only one pole and two zeros, 1, 2, 3. It is an odd number. So all the points in between 0.5 to minus 2 are the part of the root locus. Beyond minus 2, if you are taking any point beyond minus 2, to the right of that particular point, 1, 2, 3, 4. 4, it is an even number. 4 it is an even number. So no point after minus 2 is the part of the root locus. So only this much part, this line segment 0.5 to minus 2 is the part of the root locus. So darken that particular line segment. And here there is no need to draw the asymptotic lines because in the equation denominator is p minus z for the centroid and angle of asymptotes. It's equal to 0. So there is no asymptotic lines for this particular problem. Then we have to find the imaginary axis crossing point, that is by using root stability criteria. In order to prepare the table, first we need a characteristic equation. Characteristic equation is 1 plus GSHS is equal to 0. So this is open loop transfer function. Characteristic equation is 1 plus GSHS is equal to 0. Therefore 1 plus k into s square minus 2s plus 5 divided by s plus 2 into s minus 0.5 equal to 0. So that is s plus 2 into s minus 0.5 plus k into s square minus 2s plus 5 is equal to 0. Then removing the bracket, and you will get the equation as s square into 1 plus k plus s into 1.5 minus 2k plus 5k minus 1 is equal to 0. Therefore, the root array is, first we have to label all the rows starting from the highest power. Therefore, s square, s raised to 1, s raised to 0. Write the alternate coefficients, that is 1 plus k and 5k minus 1. Remaining coefficient 1.5 minus 2k and 0. So this term is this term into this term divided by this term itself, that is 5k minus 1 minus 0 into 1 plus k. So this term itself 5k minus 1. Now in order for the system to be stable, no sign changes in the first column. For that, the condition is 1 plus k must be greater than 0 or k must be greater than minus 1. Then 1.5 minus 2k, it should be greater than 0. From this, k should be less than 0.75. Then 5k minus 1, from this k greater than 0.2. So the range is 0.2 less than k less than 0.75. K minus 1, we can ignore the negative values for k. So 0.2 less than k less than 0.75. If k is equal to 0.75, then marginal stability. When k less than 0.75, system is stable. When k greater than 0.75, system is unstable. If it is equal to marginal stability. So form an auxiliary equation from the previous row, that is 1 plus k s square plus alternate coefficient 5k minus 1 is equal to 0. Put k is equal to 0.75 for marginal stability, and the roots are j 1.25 and minus j 1.25. So the root locus branches intersect the imaginary axis at these 2 points. For the marginal stability, the roots are on the imaginary axis. So we'll get that imaginary axis crossing point. Then find the breakaway point. It is the solution of dk by ds is equal to 0. So this is the characteristic equation from the previous slide. From this equation, write k is equal to. Then you have to find dk by ds and equate it to 0. Then that value, numerator is equal to 0. From that equation you will get numerator is equal to 0. From that equation you can find the values for s1 and s2. So solve for this. First find dk by ds equal to 0, then solve for the roots. So you will get two values, minus 0.4 and 3.6. Here this ball is moving. From this figure we can see that this ball is moving along in this direction. This ball is moving along in this direction. This ball cannot move in this direction because this is not part of the root locus. This ball can move only in this direction because this is not part of the root locus. So finally they will meet at one particular point. That is the breakaway point where the multiple pole exists. It is in between 0.5 and minus 2. Therefore, 3.6 is not the breakaway point. So minus 0.4 is the breakaway point. Then also find the angle of arrival to the complex zero. Here two zeros are there, complex zeros. So we need to find the angle of arrival, in which direction this root locus branch will come and terminate. So you have to find that particular angle. For that the equation is 180 minus 5z minus 5p, where 5z is the sum of all angles subtended by the remaining zeros and 5p is the sum of all angles subtended by the remaining poles. That is, we are going to find the angle of arrival for this particular complex pole. So draw a line to all other poles and zeros. So this is the complex pole conjugate. So always it will be 90. So only one zero remaining, therefore 5z is equal to 90. Then 5p sum of, that is, measure this angle, measure this angle. This angle is 76 and this angle is 34. So this is equal to 200. So the angle of arrival for this particular pole is 200. Then by symmetry, the angle of arrival to the complex zero minus 1 plus j2, it will be minus 200. So now we know the imaginary axis crossing point, that is plus j 1.25 and minus j 1.25, and breakaway point is minus 0.4, and the angle of arrival is 200 here. Here it is minus 200. So complete the root locus. This ball move along in this direction. This ball will move along in this direction. After reaching the breakaway point, one ball will move along this direction and it will pass through the imaginary axis through the point j 1.25 and terminate at this complex zero with an angle say 200 degree. Angle of arrival is 200. Here the angle of arrival is minus 200 or plus 160 or minus 200. In this way you can draw the root locus for this particular problem. Thank you. So this problem, the characteristic equation of a unity feedback system is given by s square plus k minus 1 into s plus k is equal to 0. Sketch the root locus for 0 less than k less than infinity. Find the value of k at which the system is stable oscillator. So here characteristic equation is given. We need open loop transfer function g of s h of s. So characteristic equation is 1 plus g of s h of s is equal to 0. So try to write this equation in the form 1 plus some term equal to 0. That some term will be the g of s h of s. So for that what we have to do is uh, remove this bracket. S square plus ks minus s plus k equal to 0. Then s square plus k into 1 plus s. K into 1 plus s, because we need k into some term in the numerator divided by some term in the denominator. Minus s is equal to 0. So s square minus s plus k into 1 plus s equal to 0. Then divide this term by s square minus s plus divide this term also by s square minus s. So this term will become 1 plus this term 1 plus k into 1 plus s divided by s square minus s is s into s minus 1 equal to 0. Therefore g of s h of s is equal to k into 1 plus s into k into 1 plus s divided by s into s minus 1. That is g of s h. Then identify the open loop poles and zeros. Likewise complete the problem. Another one is plot the root locus for the system whose characteristic equation is 1 plus k into s plus 2 divided by s square plus 2s plus 2 is equal to 0. In this problem, g of s h of s is equal to k into s plus 2 divided by s square plus 2s plus 2. Do this problem also.